So let's continue on our discussion of bonding. So far, we have discussed the fact the first type of bonding is with these big atoms over here. For instance, I talked about sodium, and sodium having, if we will look, 2-8-1 in terms of the electrons in their individual shells. For those that didn't know what I'm talking about, in the first energy level, there's 2. In the second energy level, there's 8. And we know 8 fills the second energy level because this is where the energy levels fill. So 2-8 shows us that 8 is the maximum that we can have, just like helium has the 2 here, 2 electrons. Okay, so in any case, sodium has 1 extra. And if you look at chlorine, if you look at the configuration down here, it's chlorine is what? 2-8-7. It needs 1 more to become as stable as argon. So as I mentioned, party people, there's a flow of electrons from the bigger atom to the smaller atom. And when electrons flow, it's a redox reaction. And the ones that lose, okay, they get oxidized. And the ones that gain, 2-8-8 now, gets reduced. And how remember that? Leo, the lion, says grr. Okay? And that's one type of bonding. And it's understandable that when sodium gains an electron, it becomes what? It becomes Na+. And when sodium loses an electron, it becomes +1 because now it has 1 less electron. Chlorine, when it gains an electron, becomes chlorine negative. And they stick together because of differences in charges. This +1 ion, no longer an atom, attracts this negative. And they stick together and they make something called a salt. And it's called ionic bonding. Okay, it's our first type of bonding. But all types of bonding between atoms results in stable electron configurations. As I said before, these atoms on this side are the most stable, low energy atoms. The atoms that are not, okay, want to become like them by having the same filled energy levels. Remember, 2-8, or filling the first and second energy level, is what neon has. That's why neon doesn't react, doesn't make any bonds. Fluorine, being 2-7, is 1 away from becoming as stable. Oxygen is what? 2 away. So it's important that you realize that bonding between atoms is how atoms who are not bonded, who don't have a what? Filled, completed outer shell, how they get a completed outer shell is by using each other. In the case of sodium and chlorine, there was something called a transfer, a redox reaction to occur in order for sodium now to have a completed outer shell, 2-8, and chlorine now to have a completed outer shell, 2-8-8. So they both used each other. And they went from high energy atoms to what? Lower energy compounds. And very spontaneous, delta G is negative. Okay, that is the first type, okay, of bonding. Now let's get into the second type. I'm just going to get rid of some of this. Now, as I've mentioned, okay, the atoms that are in this area here are the smaller atoms. Okay, they're so small they love to gain. Everybody else, okay, is a big atom, and they're so big, these atoms like to lose. So anytime you put these big atoms next to the small atoms, there's going to be an oxidation reaction or redox reaction where electrons go from the big atoms to the small atoms. And again, these things are called metals. And metals lose electrons because they hold on to them loosely. Okay, and they want to get stable by gaining enough to hopefully get to a filled, completed outer shell. That's what stability low energy is. And these, of course, are the nonmetals. All right. Now, when we had sodium and chlorine, okay, as I just mentioned, there was a transfer because big atoms hold on to loosely and small atoms do what? Hold on tightly. So the loosely held electrons go to the more tightly held electrons, as we just talked about. Now, in the example I'm going to give you, we're no longer going to deal with metals and nonmetals. Okay, if we deal with, if we talk about cellular respiration, okay, we're going to deal with nonmetals and nonmetals. That's right, the small guy. So let's make some space here and talk about the reaction that occurs, okay, with um, uh, cellular respiration. So we take glucose, C6H12O6. We're going to react it with oxygen, and we're going to make essentially CO2 and water. That's the overall reaction. Now, this reaction is not balanced. I'm just going to leave it unbalanced for a second or for a while. I'm not really talking about that today. But let's balance it. We have 6 carbons on this side, so it makes 6 of these. Okay, we have 12 H's, so we'll put a 6 in front. I'm just talking about how many of the molecules. And that's going to give us, let's see, 12 oxygen, 6 times 2, and then 6 more, okay, for a total of 18 oxygens. This is 6 oxygens here, and to get 18, we're going to need what? You're going to need, so if we have the 6 oxygens here, we need to have 12 more, so we need a 6 in front here, okay? So 6 here. And don't worry about this, this is a 1 in front. Well, this means is for every 1 glucose molecule, we need 6 oxygen molecules, 6 CO2 molecules, and 6 water molecules. Okay, no big deal, okay? Moving forward, let's talk about this. If you look into the molecules of glucose, you can see they're all what? They're all carbon, hydrogen, and oxygen. Now, hydrogen's written over here, but it's really a small metal, non-metal, I should say, so it really belongs with the non-metals. So they do write it over there, but this guy is a non-metal. So you have carbon, hydrogen, and oxygen. Well, what are they? Carbon, hydrogen, and oxygen. They're all nonmetals. And they're reacting with O2, more nonmetals. So in this case, we're going to have small radii and small radii. And the example I can give is this. When we deal with a metal, like we talked about sodium chloride, there was a transfer of electrons because this one loosely held electrons and this one gained. It's kind of like me and my son having a tug of war. Okay, to feel like a man, okay, I have the rope in my 5-year-old, okay, he has the other end of the rope, and to feel like a man, we have a tug of war in the morning. Of course, I'm so much stronger, so I pull the rope away from him. He cries for a little bit, all right, and he gets over it. I don't do that, by the way. I give him gloves. The point being is that I pull the rope away from him because me, as the nonmetal, chlorine, is doing what? Yanking the electrons away from the atom who loses electrons easily. So the atom who loses electrons easily is the metal, is the bigger atom. Even though I drew it as a small person, I can see the issues there. So the point is, that what I want to try to make a point here is that the transfer of electrons happens because the difference in strength is large. Me and my son have a huge difference in strength, so there's going to be someone pulling the rope away. However, if I'm bonding between these smaller atoms, like chlorine and hydrogen, or in the case of, let's say, hydrogen and oxygen, anytime I'm dealing with these guys over here, carbons and hydrogens and oxygens, oh my, they're going to have to force to share. An example I can give you is me and my evil twin Mongo. Okay? Yes, I have a twin, and his name is Mongo, and we have a tug of war. And when we have a tug of war, because we're twins, we have the same strength. He might be a little stronger, Mongo. Okay, he's got the hair. I choose not to let it grow long. Now, we pull on this rope, and because both of us are smaller atoms that have high attraction or high strength for electrons, we're forced to share, and that's important. So unlike the reaction I talked about previously, this reaction, we have to show sharing. So there's not going to be a transfer that's easily understood in terms of oxidation and reduction. We're now going to be forced to share. Okay, so let me explain what that's about. Okay, so let's get all this out of the way. Let's get some room here. All right, now, how do we show the sharing? And again, in order to have sharing, you have to have nonmetals and nonmetals. Who are the nonmetals? The smaller atoms. So let's think about who our smaller atoms are. Okay, they're over here. So let's look about a reaction with a smaller atom. So let's take hydrogen. We know it has 1 electron now from today. It's got 1 proton and 1 electron. By itself, it has high energy. because it has just one electron. And as we've learned, there are 2 electrons in the first row. We call them periods. There are 2 electrons in the first energy level. So hydrogen wants 1 more. Well, guess what? If another hydrogen comes by who has another what? Electron. Look at that. Because they're both what? Strong for electrons. They're both of these nonmetal things. They're forced to share. And when they're forced to share, this hydrogen by sharing feels like it has 2, and this hydrogen feels like it has 2, and by sharing, they feel about as stable as helium. So they're sharing to get their stable number of electrons or filled shells. Unlike what sodium chloride, we had to lose and gain. There still can be redox there though. Okay, so it's important you understand. For instance, if I have hydrochloric acid, hydrogen, okay, has 1 valence electron, and we'll put that there. Chlorine, I should say 1 electron in its outer shell. Chlorine is 2-8-7, so it's going to have 7 outermost electrons. So 1, 2, 3, 4, 5, 6, and 7. And look at this. Chlorine by sharing feels like it has 8, which means it feels like it's argon as stable, and hydrogen by sharing feels like it has 2. So these guys, when they bond to themselves, the nonmetals, the smaller atoms, they tend to do what? They tend to share to get stable. So where does this oxidation reduction occur? Well, as I said before, let's talk about what's happening here. Just getting rid of this, and that was probably not a good idea. Where does it occur from? Okay, well, it occurs right between the carbon-hydrogen bond, right? In glucose, we're going to have a lot of carbon and a lot of hydrogen bonds. This is really, really important, okay, that you get this. So the carbon-hydrogen bonds give up electrons that get shuttled to the oxygen. And if we remember, NAD and FAD are 2 coenzymes, which are soluble vitamins, niacin and riboflavin, okay, or water-soluble vitamins that help shuttle these electrons from the sugar to the oxygen. But it's subtle. It's not as a transfer like a sodium chloride. Let me show you the subtlety. Carbon and hydrogen have almost the same attraction for electrons. So if I was to draw it, here's my carbon and here's my hydrogen. These electrons are almost shared right down the middle. Now, when I take these and when they become water, and that's what happens when oxygen electron transport system accepts the hydrogens and the electrons, water looks like this. Here's an oxygen. It has some outermost electrons. It's got 6. So 1, 2, 3, 4, 5, and 6. And the hydrogens also have an electron. Look at this. Look how far away the hydrogens are. What just happened? And this is so very important. We're working with electrons that are being what? Shared right down the middle. And they become what? Electrons that are being held tightly right there. So what's happening is these electrons that are in the middle are free electrons. They have higher energy.
Girls lacrosse players, there is no workout today.
And these hydrogens, when they bond with oxygen, who is so much better at pulling the electrons away, like stronger with the pulling the rope, have them pulled away. These electrons are not as free. They're lower energy. So we're going from a state of higher energy electrons to lower energy, and that's how we get the energy. When you go from high energy to low energy, energy is released. Remember this diagram? And how do we carry these high energy electrons into the electron transport system? We do so by these carriers. Okay, so it's important you get that. So the oxidation reduction that's occurring in cellular respiration is subtle. We're not transferring electrons. We're just changing how they're what? Being shared. When they're shared almost equally, these electrons have more energy. They're not feeling the nucleus of the other 2, the protons. And when they're held tighter, when they finally get pulled to oxygen, they have less energy. So that's what we're doing. We're shuttling the electrons from the carbon-hydrogen bonds of what? Of glucose into water slowly so we can use it. And this energy change converts ADP into ATP. Hope that gave you a good feeling for what's going on.